you notice, electromagnetic theory may not sound straight away connected to quantum computing when I say for the first time, but once you get in and see what is this electromagnetic theory is all about, you would really know. In fact, it deals with the the dynamics of electric field and the magnetic field. So all our quantum hardware or quantum entities like qubits, they have been created and manipulated by these electromagnetic fields. Due to that, the dynamics of electromagnetic field must be understood. That's why we need to know the basics of electromagnetic theory, right? So when I go further into the justification we saw yesterday, there are variety ways of realizing qubits. The five have listed here: superconducting qubits, trapped ions, photonic qubits, spin qubits, and neutral atoms. If you notice, if you realize the qubits out of material like trapped ions or spin qubits or even neutral atoms and superconducting qubits, which are LCR circuits, in all the four of these cases, what you notice is, okay, it's a hard, like it's like a material based qubits, but the way we interact with them, talk to them, manipulate them using the light, laser light or electromagnetic light in a coherent uh, nature. Okay, so that's why the electromagnetic theory is a very, very vital. Okay, and one more thing, what we can get insights using electromagnetic theory is we could even understand the dynamics of the qubits themselves, like in the first place. The qubits are very, very fragile, as we see from the quantum computing introduction. There is a very high chance that these qubits may go rogue due to the interaction with the noise or due to the interaction between themselves, or you name any kind of environment interaction that may lead the qubits to become noisy. And how that noise is going to affect, we can understand using the theory of electromagnetic theory of electromagnetic interactions. Okay, and when it comes to processing, okay, the gates are very vital things. So in the gates also, the realization of gates is actually possible through the quantum electromagnetic fields. Okay, right? That we have seen yesterday. And when it comes to cryogenic microwave engineering, you see the transpond based quantum hardware. There is a lot of optical wavegates are involved. Electromagnetic fields are launched to them. Then how it is going to behave and how it is going to couple, that is all possible only with the electromagnetic theory concepts. Okay, so yeah, and the reading out the signal or sending the signal or embedding the signal to the system, they're all needs the electromagnetic theory description. Okay, and when it comes to processing, let's say you keep doing multiple commands and process the information through some set of algorithms. Even in that case, we would be involving various parts of electromagnetic theory, starting from electrostatics and magnetostatics, Maxwell's equation, and photonic systems. So these are the four main branches of electromagnetic theory, are very, very important in the quantum computing. Okay, so it might look like pure physics, but it's a mathematical science, the electromagnetic theory. It comes with the addition of some mathematical concepts or mathematical domains like vector calculus, the various ways of solving differential equations, dynamical equations. There may be partial differential equations. As we start with quantum physics with the particles being waves as well as material, It's a wave duality that also could be understood and explained using this wave theory, right? Wave equations, which are a part of electromagnetic theory. And some special functions we would be using to describe the solutions or derive the solutions of involved dynamical equations. So some of the functions would be 1 minute, like green functions and some boundary value problem related special functions. Okay, right? So because of all these things, right, electromagnetic engineering is a very, very vital thing one for anyone who is entering into the quantum computing. Okay, so there is a final concluding remark here. Yesterday we did, electromagnetic theory is not just a peripheral, it is a essential. Okay, so this is what we did, and later on we went on to discuss the electrostatics, starting from how the charges are going to create a fields around them. If the charges are discrete, I can count them, then how those charges are going to create an electric field in the form of a summing, some kind of a superposition, electrostatics. Okay, so in the case of discreteness, if you see discrete charges, okay, beautifully the electric fields gets added up due to each charge. Okay, field due to each charge. That is a superposition for you. And let's say if the charges are not discrete, they're continuously varying. So in that case, what we will say, continuous varying charge distributions, we would be using integration to find the electric field due to all that entire continuously varying charges. We discussed various kinds. Okay, what is that we discussed is, we discussed if the charge is linearly distributed charge. Okay, so in that case we would be doing a single integral, we will be doing a single dimensional integration. Okay, we saw that yesterday. Okay, if the distribution of charge is areally distributed, areal distribution, in that case we will be doing a surface integration. Okay, a surface integration, or you might say double integration. Okay, if the charge distribution is volumetric, okay, volumetric distribution, in that case to find the electric field we would be doing volume integration, or you can say triple integration. Okay, all the three cases we saw yesterday. Fine. So finding electric field, finding EF. Okay, this is very, very important. We saw two different cases, discrete and the continuous. In the continuous case, we have seen three types. Okay, and what we will be doing today is, we'll be going little bit in depth. Okay, right, and see how we can get more insights about charge and its distributing electric field. Okay, diverging electric field due to a charge. Okay, so now let me write down electric field. Okay, right, and if there is an electric field due to some charge, and this electric field, let's say coming from some charge, it will be diverging. What I will have is, let's say I have some kind of a thin frame, a surface. Okay, what you see here, the field lines are punching through the surface. Okay, like that. The field lines are punching through. Simply what I will do, how many field lines are actually punching through, okay, would tell me what is the strength of the electric field. and it also tells me what is the charge which is producing this electric field. Okay, so basically what we can say is more field lines punched through that surface means the electric field strength is more. Okay, so simply what you can do, you can just integrate the field lines, how many field lines going through a surface, by you just take a small tiny element dA and see how many field lines. You just take a dot product between electric field to that field line. As you can see, electric field is per small unit element per unit area. So if you multiply the area element or take a dot product, area is a vector, electric field is a vector, so we have to take a dot product. You would be getting how much field lines are going in that particular small region. But the thing I want to find out the entire region around the charge. So what I'll do, I'll take a entire closed integration. So let's say if I have a charge, I'll just take an entire three-dimensional surface enclosing this charge, okay, right? Enclosing it, which gives us the electric field lines punching through it. So that is actually called as a flux. That is called flux. Okay, right? It's called a flux. Now it is represented with the capital phi. Now, for a single charge Q, I know what is the electric field. Electric field is very simple. 1 by 4 pi epsilon naught Q by, at some r distance I am talking about, r distance, and along that r vector. But I want to find what is the flux through that the three-dimensional surface, the two-dimensional surface around the charge. What I have to do? I have to integrate E with the surface area. Okay. Now, using spherical polar coordinate system, you can find what is the surface area of this particular sphere. Okay. So, small surface element in a spherical polar coordinate system is, okay, r sine theta, r d theta, d phi. Okay. So r sine theta is one dimension, r d theta is theta dimension, d phi is another dimension. So basically, this is a small surface element dA with the r cap as a direction. Now, if you notice, what you will get, E is along the surface and dI is also along the surface. I can simply multiply that as 1 by 4 pi epsilon naught Q by r square. R cap dot product is 1. They are unit vectors and they are along the same direction. So what I'm left with is, let me remove this dA. Left with is r square sine theta d theta d phi. So r square cancels. Now what I'm left with 1 by 4 pi epsilon naught q. Now let me expand the overall integral into two double integrals because of the surface integration. So there is a d phi runs from 0 to 2 pi. In spherical coordinate system, the azimuthal angle runs on the equatorial plane from 0 to pi, if you remember. Okay. And theta is a polar angle, runs from north to south pole. It's a pi. It ranges between 0 to pi. Sine theta d theta. Okay. Now, the first term gives, the integral term gives just a 2 pi. And the second term gives you, okay, integration of sine theta is minus cos theta. And sorry, sine theta is minus cos theta. And if you substitute pi and 0 integral values, integral limit values, you would be getting this as a value 2. So, what is the result of my flux? I have calculated flux is 1 by 4 pi epsilon naught q into 2 pi into 2. So, there is a 4 pi and 4 pi cancels, q by epsilon naught I'll get. So, what is the flux going through a closed spherical surface? Okay, which is simply equal to charge enclosed within the surface divided by the permittivity of the free space, right? So it is not matters anything else, only matters is how much charge is there enclosed within that. Okay, and remember, if the charge is outside some enclosure, it is not going to contribute, because let's say some charge is outside, let's say some closed surface is there. Now the field lines due to this charge would go in and come out. So whatever is going in just comes out. So there is a positive contribution and negative contribution. So there will be no charge punching through this surface which is outside. Enclosed surface, remember, enclosed surface. Okay, right? So in order to have electric field flux to be contributed, the charge should be within the enclosure. Okay. Now the formula which we actually derived is electric field dot product with the surface area is equal to charge enclosed divided by epsilon naught. This is actually called a Gauss's law, which we have seen in a very early level of studying electromagnetic theory. Okay. Now, what you will see in the Gauss's law, right? It's an integral. Okay. So, in our electromagnetics dynamics, if you see it, we need to have some differential equations, right? The question is there any way I can convert this into a differential equation? Okay. Right? If I do it, if there is any advantage, you can think about that. Okay. Because sometimes the integration is tough to do, differentiation is easy to do. Okay. So now, just to recollect, there is a mathematical relation which converts a surface integration to volume integration. It is called a divergence relation. Divergence relation. Okay. What it does is, let's say I have a vectorial function, so vector, okay, which is integrated about some enclosed surface. The surface integral is equal to volume integration of that entire volume consisted in that surface with what element? Divergence of that same vector multiplied by the small volume. Okay, so this is a divergence relation for you. What it does, it connects a double integral to triple integral. Okay, fine. Okay, what it has to do with our case is, we have a double integral. You see, surface integral we have. Let's convert the electric field integral, whatever we have, surface integral to volume integral. Let's do that and see what we can do. Okay, so I have a surface integral E dot dA, which is going to be a volume integral del dot E with a small volume, which is equal to Q enclosed divided by epsilon naught. Now, remember, Q can be linear integral, linearly distributed. Q can be surface distributed. Q can be volume distributed. For this case, let's choose that Q is volumetrically distributed. What I mean is, Q is distributed on some clump of metal, okay, some conductor. So in that case, what I will do, I'll represent Q enclosed as equal to what? Integration over small volume multiplying the density of charge. Rho is the density of the charge. This is charge density, volume charge density. Okay. This is a volume. Let's say it's a volume integration. Now let's substitute in the above equation. What you will get? Integration over volume. The divergence of A with the d tau is equal to integral 1 by epsilon naught volumetric integration rho into d tau. Now, both sides I have a volumetric integration. I can simply equate the integrants. Okay, if I equate the integrants, what I'll get? Divergence of electric field is equal to rho by epsilon naught. Okay, you see now it becomes much simple. If I know the electric field, I take a divergence of it and I will get to know which charge it is being produced, from which charge it is being produced. Let's say I know the charge distribution. In fact, I can derive the electric field using this. So this is a Gauss's law in differential form. Okay, right? Sometimes if you are not able to find the electric field due to some charge distribution, you can use this differential form or you can use the integral form, whichever way if you are comfortable. Okay, right? Even you can cross check, take any electric field, okay, any given electric field. For example, in this case, the electric field due to charge. You can find the divergence of this value or this expression, and you can find which is equal to charge enclosed divided by epsilon naught. Okay, so in the notes I have for you, I have added for you. You please cross check. I'm not going in details. Okay, it will take some time. Okay, now, so I have seen the divergence of electric field. Now in the mathematics, this del operator is there, right? So del operator can be acted upon the given vectorial field in a divergence form or in a curl form also you can do. What is that curl is going to get or explain to you, we'll just see now. It's a very important implication. We should know that. Okay. Let's worry about what is the curl of given electric field. Any kind of electric field. For an example, I will take electric field due to a simple charge, a single charge. Electric field due to a single charge. Okay. Now I want to find a curl. Okay. Curl of this one. By the way, right? So there is a relation which also connects the linear integral to volume integral. Sorry, surface integral. Okay, what is that? Is linear or single integration to a surface integration. Okay, what is that? Is if you have some kind of a surface, instead of finding integration over the entire surface, okay, what you can do, you can just do a integration along the circumference. So your double integral is turned down to a single integral. Okay, it is called Stokes theorem. Just earlier we saw divergence theorem. So this is called Stokes theorem. Okay. So what it says is, let me show you Stokes theorem. If I have a vectorial field A dot dl, if I do it on the entire surface, is equal to the curl of that vectorial field with the line integral. Okay, right? Sorry, yeah, this is this is left hand side is a line integral. I'm sorry, the right hand side is a surface integral. Okay, right? So the circle on the integral stands for closed surface. Sorry, closed line integral. Okay. Now I've seen some like a vector multiplying into some small linear element. Okay, so I have a vector field here, electric field here. Just try to find out what is the electric field multiplying onto some dl. Okay, let me do this. It is just like a field acting from small element dl. Okay, or doing some work on the dl. Okay, so this is moving something from A to B. Like I have electric field which pushes some test charge from position A to position. Now what will be this value? Let me find out. 1 by 4 pi epsilon naught q by r square r cap dot dl. Okay, dot dl. Now the electric field and the dl always okay always have some kind of a similar length, like a similar direction. If that is the case, what I'll be having is, okay, so there were question, what is the radial component or what is the transversal component? Okay, so I think that was the question earlier. Okay, just a minute. Sorry guys, I just noticed the chart and there is a question there. Yeah, here. Now, the small volume element I have represented as r sine theta, r d theta, r d phi. Na? So, how did I get this is, if we just take a spherical coordinate system, okay, right. I'll just explain spherical coordinate system. So, this is a vector which makes angle theta with the z axis. Okay, and if you just drop a shadow of this vector onto equatorial plane, it will make an angle phi with the x-axis. Okay, now radial is along the vector r, but what is the theta direction? Theta direction is, okay, d theta is this direction. Okay, and what is the phi direction? Phi direction is along this. But I want to find the surface on this three-dimensional sphere. So, first variation is dr, right? And second variation is, I'm sorry, there is a, yeah, the first variation is dr, and second variation is d theta, third variation d. But dr I don't want because I'm confining to a surface of certain radius. So dr is ruled out. Now d theta and d phi. Now these are the radians. I can't multiply and get the surface. So if you notice carefully, if you multiply r with a d theta, you would be getting this arc length. Okay, the arc length. So r d theta would be a arc length, translational arc length, and I just want one more element which would be r sine theta d phi. So r sine theta is what? R sine theta is a arc a radial direction. Okay, this radial direction on the equatorial plane. Okay, that radial direction small element multiplied by d phi would give a wall a surface arc length on the equatorial plane. So let me show you clearly. Okay, so okay, let me write down neatly. Okay, somebody was asking, so one minute. Okay, if this is r, this is r cos theta. Okay, and this quantity is r sine theta. Okay, so a small change in phi value. Okay, right? This is a small change in d phi. If I multiply by d phi with the r sine theta, what you get? This arc length you will get. Arc length on equatorial surface. Okay, equatorial. If you multiply that equatorial surface arc length with the arc length here, what is this arc length here? This is a d theta. You multiply r with a d theta, you would get arc length due to variation in theta. and this is due to variation in phi. Okay, so this is a three-dimensional system. In the three-dimensional system, r varies as dr, theta varies as a d theta, phi varies as a d phi. But r I am not varying, I am confining on the surface. On the surface, I want to take a small surface element. What should I do? I'll find what is the corresponding arc length in the d theta, that is r d theta. In case of here, r sine theta d phi. If I multiply both of them, I'll get r square sine theta d phi. This is a surface element. Okay, I hope you understand here what I mean. What did I substitute here? Okay, fine. Okay, then let's get back quickly where we are at. We are at this point. We are trying to find what is the E dot dl. So E dot dl comes to be a 1 by 4 pi epsilon naught. Okay, there is an integral. I should not forget. A to b, okay, q by r square into dr. So r cap with the dl, okay, I'm replacing it as a dr. Okay, so small change in the away from the radial direction. I'm just moving some charge. Okay, so now this quantity, if we find out and substitute, what you are going to get is E dot dl a comma b is equal to 1 by 4 pi epsilon naught q by RA after integrating and then substituting the limits, because integration of 1 by r square dr is simply equal to 1 by 1 minus 1 by r. So a to b becomes a reverse. So b to a to b becomes b to a. That's what we'll have. Now, if you notice, if I start finding the integration over the closed perimeter, what I mean is, let's say there is some charge here, I move it somewhere and bring that same charge, test charge q, test charge q to same location. Okay, you have not done any work. Even though you lost the energy, you pick something, go on something around, then come back and put it at the same location. So you have not done any work, or you have not done anything. So if I just do a closed integration of E dot dl, is going to give you 0, because initial point and the final point is equal to 0 in the case of closed integration. Okay, so now what it is conveying for me is E dot dl is equal to 0 implies, as per our Stokes theorem, I just convert the linear integral to surface integral as del cross E with the surface integration is equal to 0. Why? That is the divergence formula what we have seen. Okay, where is that divergence? Yeah, here. So Stokes theorem what we have seen. Okay, now what is the implication? Implication is very simple. This is only 0 if curl of E is equal to 0. This is makes sense. You know why? If I have a static charge, some static charge, its field lines always goes out. Okay, field lines always goes out, diverges. They never curl around. So the curl means the cross del cross A being non-zero means they're curling around. But for a static turn okay, they never turn around or curl around. Means curl of electric field is always 0. Very, very simple. In the case of magnetic field, curl of B is non-zero, but divergence of B would be 0. That we will see it in the magnetostatics. Okay, right? So we're already late. So let me Let me go for magnetostatics, right? So now talking about E dot dl, which is some kind of a work done actually. It's something like I lift something, keeping on a table. I added a potential to the system, potential energy to the system. So basically, if you integrate an E dot dl from some point to some point, means you are bringing some charge from some arbitrary location to some specific location R, right? If you multiply that with a negative sign, which is going to be a vectorial potential, it is called electric potential. Okay, we haven't seen this earlier or during our electromagnetic theory. Okay, right? So basically, there is a relation between E to V. How? You just see, instead of taking arbitrary reason to some R, let's say I do the work from some A to B, E dot dl, move some charge with an electric field along some dl with some inside. Okay, right? What is this? This is literally VB minus VA. Okay, VB minus VA. Right? So now, as we have seen, the left hand side is can be converted into integral. How? Integration a to b del gradient of v, okay, dl. So gradient is there. If I integrate, becomes just a v, right? So on the right hand side, I have a to b e dot dl. Okay, fine. Now, just to see on both sides is a line integral, same integral limits. You can simply say E electric field is equal to gradient of vectorial potential. Okay, it's not a vector, it's just a scalar field. Okay, right? So V is a vectorial potential, electric potential, sorry, scalar potential. So, and gradient of it becomes a vector, it becomes an electric field. So you can give a relation for electric field vector V in terms of electric field as minus arbitrary location to E dot dl. For a static simple charge, you can also derive 1 by 4 pi epsilon Q by R. That's all. And there is no direction for this. Only electric field has a direction. Okay? Very simple for a point charge. So there is a technique always people do. If I am not able to find the electric field, whether using Gaussian, Gauss's law, whether it's an integral method or differential method, I'm not able to do. What I'll do, I use the V electric potential, and then I can calculate electric field. Okay, right? Fine. Okay, let me go further, and now let's talk in terms of magnetic fields. Okay, sorry, right? So we have seen current carrying wire, magnetostatics. We are venturing to statics. Okay, so I'll just give a hint, a introduction. Okay, we can go into the magnetostatics and then take a break maybe after 20 minutes. Okay, so as we have seen, moving charges creates a magnetic field around. Very simple. Okay, right? So a static charge just creates a magnetic electric field. Moving charges creates a, along with electric field, probably they will create magnetic field also. So who gave this description? You have all know. It is called Biot's-Savart's law. Biot-Savart's law. What it says, magnetic field due to some charge, some moving charge around some position R is equal to mu naught by 4 pi proportionality constant integration. How much current is going through that? Okay, and cross product with a vector connecting that surface current element to the test location, okay, divided by r square, okay. And what is the surface value line element? A small line element. So what we will do here, okay, we just take dl into current, and let's say current is a constant, so I can simply write down vr as mu naught I by 4 pi, okay, integration dl, always take prime for the test location, sorry, source location, okay, r cap divided by r square. So just like Gauss's law, here also the distance matters. If the source is very far, obviously the magnetic field strength is low there, inversely proportional. And the current strength is more, obviously more magnetic field is around. Okay. So just like absolute permittivity, I have here permeability. Okay. So this is a mu naught is a permeability. It tells me what is the resistance experienced by magnetic field lines go through that particular medium, okay, or free space in this particular case, okay. So the magnetic field is measured in terms of Teslas, that is Newton, ampere, meter, okay, or CGS units in the Gauss also, in the Gauss, they will measure, okay, right. Now, just like the current can be a linear, current can be surface, current can be volumetric. Okay, in that case, what would be the magnetic field? Okay, so we can adopt the above equation for the various different cases of current distributions. Okay, so the first one is linear. Okay, this is a linear current distribution. Okay, fine. Now I want to know for surface current distribution, what would be the magnetic field produced? Okay. Now the current is there. Only thing is now current is distributed on a surface. Let's say there is a slab, small slab is there. Current is going through. Okay. Now I can show there is a surface current. What is the surface current is? Just take a small cross section or linear cross section is just draw a line. How many field lines or current lines go through that? That is a surface current density. So the surface current density is represented by K. So K is a vector quantity. K at some r, position r, okay, is actually equal to current going to from some length here, okay. So it's a ampere per meter, okay. Now that is there. Now what would be the Biot-Savart's law? How it is going to be modified is very simple. You will have constant as usual, okay. Only thing is in the place of r I will have k, okay, r cap and r square, and instead of a small element dl I will have small surface element dA, and that is at the surface of, okay, surface of the source, okay, right. That means it's a double integral. Earlier I have a single integral. Now I'll have a double integral. Fine. So very good. Now we know for the surface current distribution what would be the magnetic field. Now the question is what would be for the volume current distribution? Okay. For the volume current distribution, what is the magnetic field? This one also very simply can be adopted from the previous case, which is mu naught by 4 pi. Instead of having a surface current, we'll have a volume current. By the way, what is the volume current? Let's say I have some wire. Okay. Electric current means charges are going through the volume. How much charges are going, we how to find? We just take a small cross section. How many lines of current going through that is a quantity, is a current density. So I'll have current divided by surface area is equal to the current density. Okay, current I is a vector and J is a vector. So in this case, what is the magnetic field would be? Instead of I, I'll have a J. Everything else is same. Okay, and I'll have a volume, small volume. Okay, d tau. Fine. So this is a Biot-Savart's law for the case of current carrying wire. It's a volume current. Very good. Now we have seen what is a magnetic field would look like. Okay, what is a magnetic field would look like? Fine. Due to different cases. Now let's say I want to know about. Let's say I want to know about what is the divergence of magnetic field. What is the curl of the magnetic field? Okay. So for simple case, we'll take a linear current carrying wire and its magnetic field. Let's say we know it. What is its magnetic field? We can use Biot-Savart's law, okay, and find out. So let's find out, okay. So there is a current carrying wire. It produces a magnetic field around. Now, okay, let's say I know B, it creates a magnetic field on some small area, linear line, okay. So which is, let's say, some dl, and B dot dl. I want to find out the entire perimeter, which is going to be integration mu naught I by 4 pi, sorry, 2 pi, I'm sorry, 2 pi, okay. And for this linear current carrying wire, you will have 2 pi s into dl, okay, where s is a quantity, okay, small linear, okay. So s is a quantity, entire length, sorry, the distance from the dl, this the line, okay, right. Now which is going to be mu naught I 2 pi s integral of dl. Okay, what is this integral of dl? Mu naught I 2 pi s. If the radius is s, you'll have 2 pi s. So 2 pi s gets cancels. I'll get mu naught I. Okay, so magnetic field due to current carrying wire, if I know, which is mu naught I by 2 pi s, and if I integrate over some circumference, I'll be getting just simply mu naught I. So I will have a formula B dot dl is equal to mu naught into I enclosed in that circumference. Just like Gauss's law, I'll have Ampere's law. Okay, right? So if I am not able to find magnetic field due to Biot-Savart's law, what I can do, I can use Ampere's law. Now we had seen Gauss's law in the differential form as well as integral form. Now we have Ampere's law in the integral form. That means, is it possible to have divergence, sorry, Ampere's law in the differential form? Of course, yes. So what we will do here, we'll be using a Stokes theorem. We have a Stokes theorem. What it says? some vectorial, some vector which is integrated on some closed circumference is equal to, instead of doing a circumference, you can find the areal integration, okay, right? Areal integration within the circumference. So, linear integration is connected to the surface integration, okay? So, linear means line, this is a surface. What I have on the above, I have a linear integration. Let's convert that into surface integration, which means I'll have curl of B into dA, okay, is equal to mu naught. By the way, what is I enclosed? I enclosed can be a current density, a volume current density. So, which is, what is J? J is I by S, sorry, I by small surface, this surface. Okay. So, what I will do now, I'll say, I don't know what, it may not be always cylindrical, it can be any shape. So, I simply say J dot small surface area. Okay. Now, if you notice on the left and right, both are surface integrals. Surface. I can just equate the integrands, okay, and show that curl of V is equal to mu naught J. This is Ampere's law in differential form. Okay, simple. Okay, so doesn't matter whether you are having a volumetric integration or a surface integration, or you have a linear integration. You can change using our divergence and Stokes theorem. There is something also called which converts directly from linear integration to the triple integral volume integration. Okay, so that we are not talking here, that may be used somewhere else. Okay, now the question is, do I have any value for the divergence of magnetic field? Okay, divergence of magnetic field. Now the question is, what the physical interpretation or meaning of divergence? Divergence means the field lines must distribute. Okay. Now let's take the obvious case. B is mu naught by 4 pi J cross R cap divided by R square and into d tau. Okay. Now what is R? What is the R vector? R vector is some test point, source point, I, test point, source point, test point, source point. So this is the R, calligraphic R. And what is the small volume at the test point? dx, dy, sorry, source point I am writing. If all primes stands for source points. So my volume is d tau is something like that. Okay, this d tau. Fine. Now, if I want to find divergence of B means, what I should find? I find divergence of, okay, what is there inside this quantity? Okay, so to start with, okay, to divergence of that, what I will be getting, okay, right? What I will be getting is divergence of J cross R cap divided by R square. This is a quantity. Now, using some product formula, for this you can show that this would be R cap by R square, okay, dot product, curl of J first, the first element, the second element, J will come out, this time we'll have a curl of R cap by r square. So this is a product formula. Now, okay, j is a function of x prime and y prime and z prime. It has nothing to do with the variation along the x, y, and z. You see, the del, whatever del you are choosing, which is a function of dou by dou x, that is an operator of dou by dou y, operator of dou by dou z, but j is a function of x prime, y prime, z prime, which means you can simply say doesn't matter what is j, which is curl of j is 0. So what I am left with, okay, what I am left with is the second term, which is curl of r cap by r square. Okay, so you already know what is the capital R looks like. Okay, if you calculate what is the curl of r cap by r square, in fact, that comes out to be 0. So, what is the conclusion? Conclusion is curl of B, sorry, divergence of B is 0. Means magnetic field lines never be straight line, never diverge. They always go somewhere and come back. Let's say I just take north and south pole, they go start and then come back. Start and they come back. Start and they come back. So they are not diverging, they are coming back to some point. So diverging means they have to go and never come back. Even though this at this point they are going out, they are going so much of length and then they will come back sometime. But their value may be very minimal, but they will always come back. So they never diverge. That is the divergence B is 0 means no divergence. The curl of B is non-zero means the electric field lines always curves around. You see, they're curling around. Okay. So yeah. Now let's have a comparison table. In that way, we will remember. Okay. So electrostatics and magnetostatics. Okay, right? So what I have Gauss's law for electrostatics. I have a Gauss's law. Let me write down only divergence form. Del dot A is equal to rho by epsilon naught. Okay. What is the curl of A? Is 0. Magnetic field lines never curl around if I take a static charge. Okay. In the electrostatics, divergence of magnetic field is 0. Means magnetic field lines never diverge, they always curl around. Curl around information is coming as curl of B is equal to mu naught J. So this is Gauss's law. This is Ampere's law. They are counterparts. Okay. Now, together, if there is an electric field and magnetic field in a region, if some test charge is moving, in that case, I'll have force created due to both the fields. You see? Okay. If electric field is there, if magnetic field is there in the region, so what is the electric field force? That is charge, test charge into magnetic field. What is a magnetic force? Okay, you can just simply say FB, which is test charge multiplied by with what velocity it is going. Okay, cross product with the magnetic field. Remember, if there is no velocity associated with the moving test charge, then there will be no magnetic force. So, to feel the magnetic field force, something has to move. There should be a velocity. If the velocity is 0, magnetic field is going to be, magnetic force is going to be 0. Right? So, you can sum both of them and write down overall electromagnetic force as, okay, Q into E plus V cross B. So this is called Lorentz force. Lorentz force. Remember, this is a force. Let's say our electron qubit is there, is experiencing some radio waves, some force due to the radio waves. This is the force, Lorentz force, it is going to experience. Okay. Now, there is a potential, vector potential. There is a electric potential for the electric field. Okay. The question is, there is a wave which gives gradient of V, sorry, gradient of V is electric field with a minus sign. Okay. Similarly, for a magnetic field, is there any magnetic potential? Electric potential is there for electric field, and magnetic field, is there any potential? Okay, that's a question you can ask. So yes, there is. Okay, which is called vectorial potential here. So what is the connection? Connection is curl of A is B. Okay, which implies the curl of B is curl of A. Okay, so we can use some product formula here, which is going to be something like this. Okay, right? Fine. If you see here, divergence of A is 0. Okay, if you choose the simplest choice, where uh, the specific current density is there, the second order divergence of A is going to be minus mu naught J, because what is curl of B, which is mu naught J. Okay, so there is a minus sign is there, so that I will send it on the right side. So the relation between vector potential to the current density is this. You can derive the solution of this equation as vectorial magnetic potential as mu naught by 4 pi integration I dot dl prime by r. Just like vector potential, electric potential, this is a magnetic potential. Magnetic potential. Okay. Now, coming back to our comparison, I have E is equal to minus del V, and here I have B is equal to curl of A. Okay, where V is electric potential and here A is magnetic vector potential. Remember that. Okay, so all these things are actually involved in like describing the interaction of electromagnetic fields with the qubits. Okay, right? So what we'll do, okay, it's 4:30. We'll take a quick break and then we'll start this some other integral technique methods, which is called uh, what is it called? Let me just give you the name. Okay, it is called finite element method for electromagnetic simulations. That we will see in the second half. We'll just take a break. After the break, I will ask some questions. Have there? I will answer those questions. Okay, everyone, welcome back. I think 5 minutes passed. Yeah. Okay, so let's see. There are some questions here. Uh, uh, Radial component and transverse component, I think I have answered. Theta is okay. There's a theta is measured from x-axis, that is anti-clockwise direction, or the others. Yeah, it is measured anti-clockwise. So let me show you that. Yeah, here you see. So theta is sorry, theta or phi you are asking. Theta measured from x-axis. No, theta is measured with respect to z-axis. K, from the north pole to the south pole. Okay. So theta is measured from north to south. So theta ranges from 0 to pi. Okay. So it can only go to the south pole. It can't go more than that. And phi is the angle measured with respect to x-axis. So it is between 0 to 2 pi. It can make one complete circle, equatorial angle. Okay, right. So R is the radial direction. It runs from R runs between 0 to infinity. But on the surface, I'm not worried about R because I'm fixing the R. So only variation on the surface I can have is I can go along the radial as an angular theta direction. From top to bottom, I can go on the surface. And I can go longitudinal. Okay, they call latitude and longitudinal. Okay, to give the location on the earth, they give latitude and longitude. Okay, right? From the North Pole between the South Pole, if you have an angle of pi radians, where are you at with respect to center? That is given by theta value. From the on the equatorial plane, if you just draw a circumference, so this runs circumference runs between 0 to 2 pi angle. Okay, with respect to x-axis, what is the phi angle? It's a longitude. It will be given. So that is the number which you usually given for the location of a person on the earth surface. Okay, same thing here. Okay. Okay, let me see. There is another question. Magnetic monopoles can never exist. Right, you are absolutely right. Monopoles can exist for a electric field or electrostatics because monopole means single charge. But magnetic field can never exist as a monopole. Okay, because you just take a bar magnet, try to break it into two monopoles. The moment you break, what happens? Let me show you that. Okay, right? So the simplest understanding, magnetic monopole never exist. Okay, that is the situation we want to discuss. Why it doesn't exist? Just take a small bar magnet, north and south. What it's consisting of? It consisting of uh, atoms with a single electrons on its valency orbit. Single electron, not a coupled electron. So, as if there is a nucleus, there is only one electron. We don't worry about other electrons inside this outermost valency orbit because they're all paired and their charge is going to be nullified by protons inside the nucleus. The only lone electron outside one valence electron, that is lone, it is not going to be nullified because the charges inside a proton can only nullify charges within this valency orbit. Okay. Now you see the electrons are revolving around this orbit. They constitute a magnetic movement downwards like a south and north pole. Small bar magnet. So what is happening here is within the bar magnet, what you see, all individual bar magnets were arranged like this. Okay, all arranged like this: north, south, north, south, north, south. Okay, so my intention was to break open, all right, make dipole into monopole, right? So I just want to break it. What happens is the moment you break, see, you see north and south, north and south, north and south. Okay, right? So the moment you break, you know what happens? All the ones at the boundary here, all the ones at the boundary here quickly interchanges this direction. They interchange in such a way I'll have two bar magnets of half a size. Okay, so here north south, north south, north south, north south, north south. Okay, north south. So there is a two magnets created, dipoles. There is a north, there is a south, there is a north, there is a south. Okay. If they were close, that time you know what happens. The south and north were together nullifies. Okay. They nullify, they attract, and they stay together. The moment you break, what happens? The interchanging happens. Okay. Right? So at this, when I try to bring them back after breaking, you can't because they interchange the direction. That time it will repel. So that time it will repel. What happens is it's completely changes. Okay, it becomes south north. Okay, there now after breaking you can't separate. So basically, having a monopole is not possible in electromagnetostatics. If there is anything somebody can come up with and detect or invent, it will completely change all the electromagnetostatics. Okay, totally magnetostatics or even electrodynamics, magnetodynamics are going to change. Okay, right? Can once again repeat measurement of theta angle in spherical polar coordinate system. Okay, okay, right? Measurement of angle spherical. Okay, so let me draw once again for your sake. Spherical coordinate system means what? I am understanding spherical coordinate system by putting on the Cartesian coordinate system. Cartesian coordinate system is I cap, j cap, and k cap. Cartesian coordinate system. Okay. I cap. Anything moving in straight lines in three-dimensional surface can be easily represented by I, j, and k. But something moving in curves non-linearly, not in lines, that has to be represented by polar coordinates in 3 dimension. So polar coordinates in 2 dimension is what? Polar coordinate in 2D. What is that? You take 2D Cartesian, if there is a r, there is a theta. So r varies in this direction, theta varies perpendicular to that, that is a theta. Okay, so this is I and j. So theta is measured with respect to x-axis in an anti-clockwise direction in 2 dimensional polar coordinate system. It is slightly different from 3 dimensional spherical coordinate system. 3D spherical polar coordinate system. Okay, here if you notice, you take any point in this three-dimensional surface. Let's say take any point. What is this point? Is connected by a distance, connected by vector from the center. So this is going to make an angle theta with respect to z-axis, north pole. So this theta can range from 0 to 2 pi only. So theta range from 0 to pi. You can ask me a question, why not 2 pi? Why not 2 pi? Because I just want to only vary theta from 0 to 0 to pi, and I want to take all the possible locations in this entire three-dimensional surface, right? Three-dimensional area, three-dimensional volume. R vector would give me distance away from the center. Theta would give me how far the position vector of that point from the North Pole, and there is a phi angle. There is the no. You just to cast a light from the top, it is going to create a shadow. This shadow, if this is R vector, and this quantity is R sine theta, this quantity is this quantity is R sine theta. I made a mistake. This is R cos sine theta. R, R cos theta. This is R sine theta. Now, R sine theta is going to make an angle phi with the x-axis. So phi is an angle runs between 0 to 2 pi on an equator. Not only an equator, you can have any surface, any equatorial surface at some other location. Okay, I can have this location. So on that location, theta can vary from 0 to 2 pi. Okay, so by just varying all these three dimensions r, phi, theta, I can span the entire three dimension. If I have to span only the surface of the sphere, there I will not vary r. I only vary theta and phi. Okay, right? So variation along r is dr. Variation along theta cap is r d theta. Variation along phi cap is r sine theta d phi. Okay, so you multiply all the three variations, you will get a volume element. If I multiply, let's say I'll multiply dr d theta. Okay, let me write down r r d theta r sine theta d phi. What you get? Small volume element. So which is r square sine theta dr d theta d phi. Okay. If I have to have a surface element on the sphere, what I'll do, I ignore the dr. So I'll get a surface element which is r sine square sine theta d theta d phi. Okay. Suppose I want to have a surface element on the equatorial plane. On the equatorial plane, you know what is varying? There on the equatorial plane, let's say theta is not varying, theta is fixed. So I have to have, let's say this is a surface. So theta is fixed. Okay, phi can vary, r can vary because r is small here, r is large here, r is small here, r is large here. So what I have to find is, I have to find a small surface element on the equatorial plane where I would be ignore theta variation. Okay, you will get the surface element there, but as of now, our case, it's not required. Okay, fine. Okay then, so let me go the other thing which we are supposed to do for today. Okay, let me save this. Okay, I can do it later. Okay. Hmm. Wait a minute. Why it is cutting? Okay, that's fine, I think. Okay, so I'm supposed to discuss this topic, which is finite element method for electromagnetic simulations. Let me tell you one thing. It is a simple idea of solving differential equations. That's all. Nothing more, nothing less. Okay? Right? So, let me write down. This is what? Is a numerical approach. Numerical approach. Okay? To solve partial differential equations. Partial D. Okay? Right? Just a minute. Yeah, sorry. Okay, so finite element method for electromagnetic simulations, which is in fact a numerical approach to solve a partial differential equations. Okay, so one such special case is there in the wave equations in modeling electromagnetic circuits. Okay, what is a wave equation? I'm just bringing a new thing. Okay, wave equation is electric field and magnetic field varies in space, in time, okay? And that variation in space and time actually is connected to the energy of electric field, energy of magnetic field flowing along that space in and in time, okay? So which is written as del square E is equal to plus, 1 minute, okay, del square E plus 1 by C square dou square E by dou T square is equal to 0. So this is the wave equation for electric field. Okay. It shows how the variation of electric field happens in space. Okay. Spatial integration as a derivation and temporal derivation, how electric field varies in time in a particular location. So that is connected. It's a wave equation. It tells me how the wave travels in the space. Now, let's say I have a wave equation corresponding to some electric field. We want to understand what is that electric field distribution is. I need to solve this differential equation. It is in space as well as in time domain. It is a differential equation I need to solve. Okay, right? So it's going to be not easy because it's a three-dimensional space derivative is there, one-dimensional time derivative is there. Altogether, it's a four differential equations are couple differential equations. Differentiate derivatives are there. I want to solve them. Okay. For that, I I can't do it I can't do it as analytical methods. We use simply differentiate or integrate or be given a function, right? So analytical solutions are very complicated, not at all possible to get. In that case, we will do some numerical integration using some programming. Okay. So the comprehensive exploration will be done using something called a mesh generation. Okay, mesh generation and we'll be using some basic functions and computational techniques used for solving this Maxwell's equation. Okay, basically Maxwell's equation we just saw earlier. Okay, we just saw earlier divergence of electric field is rho by epsilon naught. Curl of E is equal to 0. Okay, curl of B is equal to mu naught J. Divergence of B is equal to 0. If the electric field is not varying in time, let's say if electric field is varying in time, you know what happens? There will be a quantity coming over here, mu naught, okay, epsilon naught dou E by dou T, okay, right? Yeah. So similarly, I'll have some quantity here, but right now, these are the set of four Maxwell's equations, okay? So if I use those four Maxwell's equation and I can derive the wave equation, okay? So what I have conclude would like to conclude here is just to get the details or insights of this differential equation, I have to solve them. Analytically is possible, not possible. Numerically we can do by doing something called a mesh generation. What is a mesh generation is? Let me go further. Okay. Let's say I have I have a function, a solution of okay. I have some differential equation whose solution I'll just get some function. Okay. And if that function is something like this, okay, right? Now, what I will be doing, I'm just going to divide that into parts, okay. Numerically, I'm going to find out, given a old point, what is a new point? Given a old point, what is a new point? So it is like a iterative method. In that way, we can solve it, okay, right? So that is a finite element method with small elements we will be taking. So let's go a little bit deep. Now the question is, why finite element method for electromagnetic field is required? If you notice, Maxwell's equations yield a partial differential equations that are exceptionally difficult to solve analytically for a complex geometrical configurations and material distribution. We will be involving different kinds of waveguides. In the case of our cryogenic based quantum computer, you see coaxial, very nice uh, cylindrical waveguides. Probably for, let's say, a photonic based, there maybe we may have different kinds of waveguides which send sunlight through. So in all those cases, different configurations of coaxial cables and optical fibers, waveguides are involved. So in those cases, how this electric field actually travels, okay, how it gets confined by these different structures, guiding different structures, one has to know. Since they are complicated, we can't solve them. So we can use this finite element method. Okay, right? And there are some advantages here. Okay, and it can be applied for curved and irregular geometries. Beautiful. And if the material is not uniform, it can be inhomogeneous. Inhomogeneous. Some places it is maybe dense, some places it is maybe less dense, very light, fluid. Even in that case, we can use this finite element method. Okay, and resonant structures, obviously all the systems which we may take are resonant. And local mesh refinement means there are locations where the field is changing very dramatically. In that case, we can increase the tininess of the mesh, means more mesh elements I can take. There is some locations where the electric field is not varying much, so I'll take a much larger element. Okay, that is possible in this finite element method. Okay, so this finite element method excels through understructured measures that enable high accuracy while providing local refinement capabilities where electric and magnetic fields change rapidly. That's what I mentioned just now. Okay, fine. So let's go further. FEM computation as a finite element method in computational electromagnetostatics. Okay, right? So here, what you notice, noise. 1 minute. Okay. Uh, this finite element method forms a computational backbone for industry standard electromagnetic simulation software, including like COMSOL, most of you heard about. There is something called HFSS and CST. Okay, those cases also, this method is being implemented. Okay, for example, radio frequency wave devices, high frequency circuit analysis and characterization for modern wireless systems is possible with this. Okay, for example, if there is a filters and a couplers are involved in the communication, we can do a precision design of passive components with the complex frequency responses using this FEM method. Okay, and there are antennas also involved in signal processing, your, for example, radio frequency. In that case, radiation pattern optimization and impedance matching we can do for have a better connectivity. Okay, right? So the waveguides, as I mentioning from quite some time now, mode analysis and propagation characteristics in guided wave structures is possible by having a solutions analyzing from this FEM methods. Okay, so for example, method that solve time harmonic Maxwell's equation in the frequency domain is given in terms of this equation. Okay, so this is in a way it's a combination of a combination of Maxwell's equation. There is a curl of B is involved. Okay, so basically what is this equation is, you just take divergence of E is there, E is equal to rho by epsilon, it is there na? You just take a curl of this entire equation. Okay, and by the way, as we know, curl of E, when there is a variation in the magnetic field, in that case what I will have, minus mu naught epsilon naught rho b by rho t. Okay, right? So you can use a product rule here and obtain this equation. Okay, so we are not going into the details how are we going to obtain, but that's just an idea how do we solve using mesh FEM method. Okay, so for example, there is a mesh generation strategy. There are various ways of mesh generation strategy. I can generate a mesh using some triangles, or I can generate a mesh using some rectangles. Okay, for example, I want to cover the entire circular surface in the integration. Okay, let's say there is a function which is x square plus y square is equal to 1, or some radius r. Okay, so in this case, I want to find the area of this function, area within this curve, which is pi r square. So this is the most obvious case. I can create small triangles in the form of mesh and try to find the each area and then keep adding up. Or I can do rectangles. But always there is a problem of error, losing some values, but those can be taken care if I reduce the mesh element size. Okay, right? So, like I said, I can have a line segments for transmission lines. Let's say some lines are there. I can divide that into small elements and then start counting them and find out overall length. That is a line element. For a surface, I can have triangles and quadrilaterals for planar structures. That is what I've shown. For example, in the case of 3 dimension, I can have tetrahedral pyramids, prisms, and the hexahedral elements. So that is what is there in my very first slide. This one, tetrahedron and 8-node hexahedral. So these are the small elements I can take. I can find the entire volume by creating the small element meshes and count them, how many are there. Knowing each one's volume, I can find overall volume inside a particular enclosed surface. For example, in the case of Gauss's law, right? Okay. Yeah. And yeah. Right. So basic functions, the building blocks here. Okay. In this method, first you have to define the fields at each point and each vertices. Okay. And then construct hat shaped interpolation function centered at each node. So the field approximation has to be done. Okay. At each location. And then you can extrapolate to find out overall fields throughout the mesh and then throughout the entire volume. Okay. For example, here we are doing discrete, and if there is a continuous thing you have to do, discretization, intuition, we can follow. What is that is? Continuous function is approximated using a discrete nodal values through piecewise polynomial representation. Let's say one example I can give you. Okay. Suppose let's say I have a curve like that. Okay. If I have a curve, what I will be doing is I can approximate like this. Okay. Right. So that is one approximation. So what I am doing, I'm just dividing into parts. And if I want to find the area under the entire curve, I'll find what is this area, what is this area, what is this area, what is this area, and so on. There is a error is there anyway. Sometimes it adds up extra volume, extra area. Sometimes you loses some area. That is a error anyway. I'm sorry. You can even go hybrid. Sometimes you can take a triangle. Sometimes you can take a rectangles or squares. Okay. Fine. So this is a weak formulation, so we're not getting into the details. There is no time. I think I have to wind up now. Uh, Matrix assembly process. This is one of the method. Okay, so you people can go through it, and I'll attach one nice thesis on this FEM method. You people can refer if somebody is interested in solving the differential equations using FEM method. Okay. So anyway, boundary conditions of a differential equation plays a vital role as usual in solving. Here also it plays a very vital. Okay, so this is a summary. Okay, this is a summary of this FEM method, complete FEM workflow. What it consisting of is uh, first you define, check the geometry of the structure of the function, and then you import the required the meshes. Okay, and you design the mesh, and the basic function interpolate and extrapolate you do, and some approximations you will be doing. Okay, that is called applied Galerkin method, and then assemble you some matrices you are going to form, and you find the solutions. Okay, based on some boundary conditions. Okay, and if you have some existing results with your method, you can always cross check and find how accurate your solutions from this numerical integration of FEM. Okay, right? So that is about this. So what you can take home from here is, okay, the simple integration using like dividing the entire function or the curve into parts, and then summing up areas under the curve and finding the value. That is the finite element method for electromagnetic theory. Okay, fine. So I'll stop at this point. It is 5:13. So we started about 5:16 or so. So if there is any questions, I'll take. Sorry. If there are no questions, what we'll do, I will share both hand notes for today as well as yesterday itself I have saved 1 minute. Yesterday I have saved to Canvas everything, uh, the entire the nodes of electrostatics and magnetostatics. It's a very lengthy, about how many pages? Let me tell you, about some 50 to 50 pages at least. Okay, so it's derived for each and every case. You people can go through it, and you can refer to it. Let's say you are teaching something, you can refer to it for your students. Okay, so yeah, so I'll be uploading the entire thing to the drive. Okay, so looks like there are no questions. Okay, so we are at more or less at the end of this QT-03 and 04. Okay, so you will be having three more. It is tomorrow, day after tomorrow, and 29th. Okay, so 29th you will have hands-on with a KISS kit, right? So QT-03 and 4 would be winding up by then, and see you people in QT-05. Okay, right? So happy learning with the remaining few days, and keep up the good fashion, your passion towards quantum computing, and we see you people in the QT-05 and 6. Bye bye.
So, thank you so much, Aswat sir. Uh,
Thank you, Vikranta.
so, uh, Today we all are having some either projects presentation going on. Like Aswat sir himself is having some presentation at IIT BHU. So, and many of us are also submitting ERG. So everyone is busy in that one. But anyway, I think all the questions are already discussed. So there are no questions left. So thank you so much, sir, for your insightful session. And thank you all the participants for having this engaging session, putting your questions and having thorough discussions on that one. So I thank all the participants for this their participation. So thank you so much, sir. So I would request participants to join. We will be joining tomorrow at the same time. Uh, and definitely, many of you were asking about the quiz 3. We are requesting for that one. If they permit, if the higher authority permits to reopen it, we will soon reopen it so that everyone will get their certificate in due course. So thank you once again. Thank you, sir. Thank you so much.
Thank you, sir.
Bye,
Thank
sir.
you very much.